I know why you didn't want to hear about it, because it was tough. I put up something called, I want to explain it, I put up something approximate curve. I think at the most part, now that the more I think about this, I did it quickly before class yesterday. I want to, cancel, I don't think it's very useful at all. The idea was just to give you a baseline. This is the minimum where you're going to be in terms of grade, but I don't think that's very useful because it's probably going to be a bit above that, like a chunk above that. So, but how much, that's hard to say. So, I think I might scrap that and say something more along the lines like this. If you want to know where the boundaries are, I'm just going to distributions. But it's not based on distribution, it's more about like thinking about how many problems you had to get right to get a certain point. I would say anything above 12, believe it or not, 12, 14 is an A, roughly. Anything above 10, roughly, is a B, roughly. And anything above 6 is a C, roughly. Okay? So, I'm not holding to that. So you can't, that's just to give you a ballpark. And the reason I'm telling you that is because if you got a 6 on this, you were probably pretty freaked out. And I want to have it so that this is the reason I curve. This is the whole reason I curve. Is I don't want people giving up on me. Okay? I want you to enjoy this class. And I know that how much, I know it's a crazy word, separations and joy. I know those, but I know that you really dislike it when you think you're failing. Okay? And I want most of you, which is, that's the point of me telling you this, and I'm not going to fail most people in the class, okay? That's just the way it works. Most of you aren't failing, okay? And just to let you know, if that's you, again, even that's not, because of that huge, anyway, just the point is, I want everybody to stay engaged and everybody to believe they're going to get a good grade in this class, okay? That was a tough exam, okay? That's enough, I don't have to say anymore, that's my point. Because I know that when you think you're all failing or getting lower grades than you're used to getting, you're just going to tune out and not come. And that's what I don't want. I want you here. The exams will get easier, this one was tough. Fair enough? Okay, well that's not fair, but the point is it's getting better, okay? I understand. This is where curves help distributions, is that I will give you better grades rather than bringing you down, okay? Because I want everybody to, again, feel involved in the course. Okay? In other words, okay, for those of you who weren't here, not many people got number 1 right, okay? Not many people got number 1 right. So, there are some celebrations around the room, but the point is, there are probably few, because it was very small, the number of people who got number 1. And that just makes a huge skew in the numbers, and that's what I've got. Okay? All right, let me move on. I hope to not have anything like that on the next exam, but that's another story. Okay? I actually spent a lot of time making that exam to hopefully not have that problem, but it's actually very hard to write an exam. But you don't have to think about that. Just how do you make it so that it's fair and test what you want to test. Okay. Okay. So we're in homogeneous azeotropic distillation. And we got as far as drawing the ternary picture and the basic residue curve. I think a lot of things probably flushed out of your brain, so let me at least try to bring you back to this spot. Ethanol and propanol, methanol. And I'm not gonna do this sporadically, I'll just tell you. So remember we said this was the light boiler, and this was the heavy, in all cases, so that our residue curves in this direction always went from right to left, because methanol has a boiling temperature of 64.5 BC, and propanol has a boiling temperature of 97.2 BC, and ethanol has a boiling point of 78.2 degrees. And where this got confusing was up at ethanol, clearly all the residue curves go from methanol and propanol, but at ethanol it goes up and down, so it means what we have is a saddle point. and that the residue curves look something like this. Meaning that if you had a simple still, no matter where you are in the ternary space, you'll end up with N-propanol at long times. If you had a binary mixture of methanol and ethanol, you'd end up with ethanol. A binary mixture of ethanol and then propanol, you'd end up with N-propanol. If you had a pure component, obviously, of methanol, ethanol, or propanol, you would end up with a pure component when you started. Okay? And I gave you some rules. The tangent to the vapor equilibrium line, they don't cross. Steady states occur at all pure components and azeotropes. And they're tangents to common lines. You can see these are all tangent to each other. Okay? So we wrote those rules down. And then I told you that what we would do in this lecture was sketch residue curves. And I told you why this is important. Useful in preliminary design. Because they define feasibility. For example, can we use a simple one feed, two products column to make ethanol? Can we make ethanol for the two column, where the column looks like this? Now, we can have side columns. We're not going to get into that right now. I'll get to that later. But with a single two-product column, we can make methanol as the what? Is it going to be the distillate or the bottom? So if we're going to have a ternary mixture, we're going to have ethanol. Methanol's product. It's going to be the distillate. And propanol can be made by a two-product column. And if so, what is it? It's the bottoms. Okay? For example, if this is your feed, you want to make N-propanol, that's the distillate that would come out the top. And if you want to make methanol, this is the distillate, and the bottom product is that. This is what we talked about before. This is an indirect and a direct column. Okay? We talked about that when we were doing ternary. So we can also, there's going to be other elements of feasibility that we're going to get to not very far down in this lecture today. Okay? So feasibility is the key to this. So when we're doing these, we're even less precise than we were doing with Cape Deely. The Cape Deely gave us a rough idea of how N related to R, so reflux ratio to number of stages. Here we're not even dealing with that. We're just saying, can you make this separation by distillation? We're going to be able to answer that question. And that might not seem like an important question, but it is if you're trying to pick containers. If you know you want to separate two products and you want to add a third, will the third product work, for example? Will the third species allow you to separate the first two? Okay. It's based on incomplete data, meaning I drew that knowing the boiling points. But if you really wanted to create these curves, what would you have to do? If you really wanted to get the actual shape of these curves, you'd have to, it's the answer to all these kind of questions. Do an experiment, okay? So to actually do this, you need an experiment. But it's going to be an incentive, so these are going to give an incentive for further experimentation. In other words, the exact shape of the residue curve is going to affect the cost of the process. But if it's not even feasible, it's not even worth figuring out what the actual residue curves look like. So this sketching method is based only on boiling points. Of pure components and azeotropes. Notice I don't have any azeotropes there. We did a binary azeotrope in the last lecture. So that's all you need are the boiling points, and it allows us to draw these kind of general topology pictures. Okay? All right. So I'm actually going to tell you the method, this sketching residue curves. define each point as a saddle or a node. Right? So we're going to define a bunch of variables, and these are just counting variables. They're very simple. We're going to take all of our pure components. We're going to take our binary azeotropes, and then we're going to introduce something that you haven't seen before. We're going to have ternary azeotropes. A binary azeotrope is an azeotrope like you've seen before. Ethanol and water have a binary azeotrope at 95%. Ternary azeotropes just mean that there's an azeotrope between all three components. Okay? And we're going to count them. Are they nodes? And I'll explain this, or saddles. Actually, I can explain this right now. A node is a stable node or an unstable node. I just erased them, but the open and closed circles. A saddle is the open square. Okay? You're just going to count them up. We're going to count them, put them into that variable, N1. We're going to count the number of saddles and call it S1. Number of nodes is N2. Saddles is S2. Number of ternary nodes is N3. And the number of ternary saddles is S3. N1, N3, and S3 can be determined from boiling points. And I'll explain that in just a minute. And, okay, by these rules. Rule 1. If the arrow's on a binary edge, both point towards the vertex, both point away, toward, or away from a vertex. It's a node. Otherwise, it is a saddle. In other words, if both of the residue curves on the binary edge point up, it's a stable node. If they both point away, it's an unstable node. And if they point in opposite directions, it's a saddle. So just by counting those, the pure components in a ternary system are always the corners. We can now determine N1 and S1. Okay? We're just going to count them up. How many nodes and how many saddles? We're going to say we have 1, 2, or 3. Sorry, 0, 1, 2, or 3 nodes, and 0, 1, 2, or 3 saddles. That's all we're going to do. Okay? So this is good. This number, N1, is either 0, 1, 2, or 3. In a ternary system, saddles is 0, 1, 2, or 3. That's all there's to it. Okay? It's going to add up to the number of pure components. I will do lots of examples. Okay? Lots of examples. Ternary azeotropes. Clearly, if there are none, then N3 is equal to S3 is equal to 0, obviously. Okay? Then we have to do, let's see, how do I want to do this? gotta be a better way to do this. Every year I explain rule 2, and no one gets it at first. Let's see, let me think about it a second. Okay, so I'm going to define some things, so this is going to be rule 2. B is the number of binary isotopes. Okay, just count them up. How many binary isotopes are there? In most cases, ternary azeotropes are nodes. A ternary azeotrope is a node if A n1 plus b is less than 4. Okay? So the number of pure component nodes plus the number of binary isotopes is less than 4. Ternary isotopes are node. Or B, the ternary isotope is the lowest, second lowest, highest, or second highest boiler. Okay, so there are 4 cases there. It's the lowest, second lowest, highest, second highest boiler. If it's any of those, it's a node. Okay, so it's a node if either n1 plus b is less than 4, or it's the lowest, second lowest, highest, second highest boiler. In all other cases, it's a saddle. Hang on, I will draw pictures and it will become clear. Let's see. Okay, let's just do this one. So there are lots of examples. Let me make this bigger. Hexane, methyl acetate, methanol. This is 64.5 degrees C, 69.2 degrees C, and 56, breaking that rule there, 56.9 degrees C. So this is the lowest boiler. There's a ternary and 3 binary azeotropes. What does that mean? So let me explain that so you get used to it. That means that hexane, if you mix hexane and methanol together, they have an azeotrope. If you mix hexane and methyl acetate together, they have an azeotrope. If you mix methyl acetate and methanol together, that pair has an azeotrope. And when you mix all 3 together, there's an additional azeotrope within the middle of the triangle. Okay? So this system has 4 azeotropes. Okay? So in some ways, I've just shown you something you've never thought of before. Okay? Because you're thinking, okay, binary, we have an azeotrope. You thought an azeotrope is something that's existed between. Well, when you have 3 species, you can have 4 azeotropes. Okay? Or more. Yes?
So would it be 3 binary isotopes and 1 ternary?
Exactly. That's right. 3 binaries and a ternary. Okay? The ternary azeotrope has a boiling point of 48.2 degrees C. The binaries are 50.5 degrees C, 52.3 degrees C, and 50.5 degrees C. What are all of the binary azeotropes in this system? Are they minimum boiling azeotropes or maximum boiling azeotropes? Raise your hand, say it loud. Go ahead. Minimum boiling azeotropes. Why? Can you explain? Perfect. That's exactly it. They boil lower than the two components. Okay. So remember, you could create a system where you're going to try to separate methyl acetate from methanol. You mix those two together, this could be minimum boiling azeotrope for the other species. Okay. So first of all, let's figure out what the binaries. We're going to save those for a second. Okay. Whether those are saddle or node. When we lay this picture up, I need to give you a couple more rules. But we can do the pure components, and we can do the ternary right now. All right? With the rules that I've given you. First of all, rule 1. Let's look at the pure components. The residue curve on this binary axis. Don't even worry about the triangle right now. Just mix hexane and methyl acetate. Which way does the residue curve go? Down or up? From this azeotrope to hexane. Go ahead.
Goes away from the azeotrope
Okay, can you tell me why?
because it's a minimum boiling and residue curves. All residence curves always go towards that higher part.
The temperature always increases along the residue curve. Let me say that one more time. Temperature always increases along the residue curve. Okay, so it goes up here. What happens in the section between the azeotrope and methyl acetate? I know you know the answer, just hold it. Someone else? What happens in the section below the azeotrope? Which direction does that residue curve go? Up towards the azeotrope or down towards methyl acetate? Someone else? Yeah, go ahead. Down towards methyl acetate using the argument that has a higher temperature. Okay, it's simple. Yeah, okay. But let's just, everybody keep going here. Now, this pattern's obvious since these are all minimum boilers, so let's just go through it carefully. Does this go up to hexane or down towards the hexane methanol azeotrope? Okay, up to hexane. And beneath the azeotrope, does it go down to methanol or up to the azeotrope? At the bottom, does it go left towards methyl acetate or right towards the azeotrope between methyl acetate and methanol? Left. Okay, now hopefully you're getting the hang of this. And then from the azeotrope to methanol, does it go to the right or to the left? Right. Is everybody following along with that? Anybody lost on that? Good. Okay. I know it's straightforward. Now, following rule 1, if you're going to look at your notes, try to remember. What are the pure components in that unusual system? Are they saddles, stable nodes, unstable nodes? Don't worry about what's happening in the rest of it. You can answer that one question. Okay, you don't have to figure out the whole picture. Go ahead. Yeah.
Stable nodes.
Stable nodes. Okay, they're all stable nodes. This is an unusual system in that if you put it into a simple still, depending on where you start, you can end up with all hexane, all methyl acetate, or all methanol. Okay, now to confusing rule 2. Have a look at the ternary. What's B? So B is the number of binaries. How many do we have? 3. So B is equal to 3. Now, N1 is equal to what? How many pure component nodes do I have? How many of those pure components are nodes? Either unstable or stable. Okay? Say it loud. Raise your hand. Say it loud. 3. Thank you. How many are saddles? We don't need it for this, but how many are saddles? None. Okay, so we have no pure component saddles and 3 pure component nodes. Everybody with me so far? Okay, so N1, S1 done, because just by looking at the boiling points. Got it? Okay, straightforward. So is N1 plus B, N1 plus B clearly is 6, okay? I don't do that. Is it less than 4? No. So by point A, is it a no? No, no, it's a node if that's true. So that's not true, so, yeah, okay? B, is the ternary azeotrope the lowest, second lowest, highest, or second highest boiler, and out of what? Out of all of these. This is where that rules make sense to drawing. Including the 3 pure components, the 3 binary azeotropes, and the ternary. Is it the lowest, second lowest, highest, second highest? It's the lowest. So therefore it is a no. It's a no, okay? If this is true, if it's less than 4, it's a no. If it's one of those 4 things, it's a no. Got it? If it's anything else, it's a 7. It's a little confusing. More examples will help. I'll get there. Yes? Not both, or. Sorry, it's small. Wait, hang on. Or. Okay, or. Either one. Either one or both. It's a no. So, what is the ternary azeotrope in this system? It's a node. What kind of node? Anybody want to guess what kind of node the ternary is? Unstable. Okay? I'll just draw it as an unstable. And then, just to finish this off, what's N3? There's only one, so it's either 0 or 1. Those are your choices. It's not complicated. What's N3 and what's S3? How many nodes do we have? And how many ternary saddles do we have? 0. Okay? So we filled in most of this chart. Now, the question is, what's N2 and S2? Once you know that, you can draw the whole picture. And I can draw all the residue curves. Okay? I have to give you another rule. So based on the topology, and I'm not going to get into this, you can look at it, it's actually quite interesting. So this is just topology of lines. Okay, this is just a mathematics of how lines work. But there are 2 relations about N2 and S2. Obviously, N2 plus S2 has to equal B. Okay? And from the topology, you could get the 2 N3 minus 2 S3 plus N2 minus S2 plus N1 is equal to 2. Where it comes from, don't worry about that for now, okay? We can rearrange this, and it gives us these nice relations. It says that N2 is equal to 2 plus B minus N1 minus 2 N3 plus 2 S3 all divided by 2. And that S2 is just equal to B minus N2. Okay? So how is this useful? Well, it's quite useful because it allows us to figure out what our binary azeotropes are. In this case, for this one, N2 is equal to what? It's equal to 2 plus 3 minus N1, 3 minus 2 times N3 minus 2 times N3, which is 2 times 1, plus 2 times 0, all divided by 2, and that is 2 minus 2, 3 minus 3, wait, let me draw, have I done wrong? 2 plus 3 minus 3, I've minus 2 twice, sorry. Okay, so you get 2 minus 2, 3 minus 3 plus 0 divided by 2 is 0. So the S2 must be equal to 3. Okay? What does that mean all those binary azeotropes are? Okay. Now, you ever thought you'd be drawing patterns, okay? What do you think that looks like? Keep this in mind. Residue curves have to start from unstable nodes. How many do we have? 1. And they end where? Stable nodes. What do you think happens around those binary azeotrophs? Think about it a little bit. Do things end? Remember when we had the picture up here? Did any of the residue curves end at saddles? What does it do? Can you give me a word for it? Say that loud, that's what I want. It approaches them. Try it. You can't clicker trying it, okay? So try it. How many people have it drawn? Have a clue? Anybody guess? A guess? Yeah, go ahead. Tell me. I'll get you the next one. It's gonna be another one. Go ahead.
So there'll be 3 lines going out from the ternary azeotrope out to each saddle point.
No. Oh, without each saddle. Not quite. Well, in the back.
It'd be 6 lines coming out of the middle.
Oh, okay. Let me just add something here. There's an infinite number of lines.
Well, I mean, like 6, like, kind of boundary defined lines.
Okay, go ahead.
And then there's gonna be 1 on either side. You're gonna head towards the binary azeotropes, 1 on either side. They kind of split down towards the.
Yep. Okay. So what he's saying is going to do like that,
Yeah.
and then where are they going?
1 goes down, 1 goes up, all the way to the very components.
Like that,
Yeah.
and you got to do it 3 times. Okay. There are also, just to fill in the space, that they just connect directly, so there's nothing, residue curves go straight like that, as far as you can tell from the information you have. Notice the arrows go this way, okay, make sure you put arrows on them, they have directionality. They're not just lines. If you wanted to add more, just to make it, it depends, it's up to you, these are just representational. Don't make it too crowded, but obviously there's an infinite number of those. Okay? It's really just to give an idea. How many people had something like that along those lines? Yeah?
We find our binary azeotropes as saddles, but
Yes.
these squares.
Those are open squares, and that's just my notation, so just they're open squares. Can you not, I didn't erase well enough, did I? It's tricky. This board's not very friendly. Open squares, okay? Yes, but it's really just, the book doesn't keep to that. It does sort of, but not much more, less than I will, okay? And I'm doing it more just because I think it's helpful to keep the same notation. Okay. Tell me your name in the back, sorry. Patrick said an interesting word. What is happening here that's beyond just kind of a nice flower picture? You used a word that I want you to come back to. Do you know what it was?
Boundary.
Boundary. Okay. Where are the boundaries in this? Can you see them?
It's like a straight line from the ternary azeotropes to the
Yes. There are boundaries like this. I can have other colors. I forgot my second color set today, okay? But there are 3 boundaries, which means that there are how many different distillation regions in this picture? 3. Let's think of it this way. 1. The numbering of these is arbitrary. If I had a feed, I put a simple still, and I started anywhere in region 1, what will I end up with? At long times, at long warp times? Pure hexane. If I'm in region 2, no matter where I am in region 2, anywhere in region 2, what am I going to end up at long times? Methyl acetate. If I go for long times, okay, you get the picture, okay? It's going to go to methyl. Okay? So, can I use, for example, let's just think about this for a second. Is hexane a useful entrainer to break the methyl acetate methanol distillation boundary? No. Is any of these useful as an entrainer to break the other binary azeotrope? No. Not in this case. Yes?
Is it just a coincidence that 2 of the binary azeotropes are at the same
Yes.
temperature?
It's just a coincidence. And in fact, if you measure it, they're not exactly. It's just it's less than a degree different. Or less than 1/10 of a degree different. Okay? It probably will never be the same exact same temperature. Okay? But for this example, it doesn't matter. There are some examples, and you'll see there's one where you have to get the 100th in order to figure out what's happening. Okay? But for here, we don't need to know that. Okay. So these define distillation regions. Which have a couple of simple rules. They each contain one unstable node. Does each one of those regions have an unstable node in it? Yes. They all have quaternary in them. Okay? They all have one stable node. For that particular picture, they all have one as the stable node. The pure component, okay? And at least one saddle. Meaning they can have more than one saddle, okay? There must be one saddle. Oops, on at least one end of every distillation boundary. Is that the case? Is there a saddle on one end of every one of those boundaries? These rules are helpful when figuring out where the boundaries and regions are. Okay? A lot of times, I think they're pretty obvious. These help. Okay? What was I going to ask? Okay. What if you do distillation? Let's say I'm not going to quite get into mass balances yet, but I want you to think about it a little bit. Let's say I put a feed here. Mass balances are still straight lines. Okay? What are my choices of products? Do you remember what the products were when we had the ternary, without any boundaries, without any azeotropes? What could I have as the distillate? The lightest, which is, what's another word for the lightest when we're doing it this way? It's not always the lightest, it's the, which is the, say that's what I'm looking for. The unstable node. So we can make the unstable node into the what? If we do distillation, we can make it the distillate. or we can make the stable node into the bottoms, okay? So if you look at these, yes, these are trapezoidal now instead of triangular, but the choices for products are the ternary and the stable. The ternary and the stable, the ternary and the stable, for any feed inside this space. Does that make sense? So the choices of products are always still the unstable nodes and the stable nodes. You can't make stables for the same reason you can't make stables in the ternary. I'll explain that in more detail in a further lecture. Okay? I just want you to think about that. Be aware of it. Okay, let's do another example. Can I erase, do you want me to erase this? Can everybody have that? Yes?
The boundaries, are they going to be straight lines, or is that just coincidental?
Ah, good question. When you do sketching, which is what we're doing here, you have no information to make them curved. All you know is that it goes through the ternary and through the saddle. So in that case, they're straight lines because you don't know anything else. If you did the experiment, you might find that they're curved. Okay? However, in determining whether you can use hexane as an entrainer, does it matter whether it's curved or straight? Okay? So from a this is why they're good for feasibility. It allows you to answer the feasibility if you just assume they're all straight, but they could be in reality curved. Does that answer your question? And the curve, anyway, I'll get to that. Okay? That's way more. Let's just leave this like this. Okay? Do a different one. Methanol, methyl acetate, chloroform. .5 C, 56.9, 61.22. Again, 3 binary azeotropes, 53.76, 53.36, and 64.7. What's happening here? Notice anything? Notice here I added more decimal points so you can see those binaries are different. What's the first thing you notice here that's unusual? Yeah? You have a maximum boiling azeotrope. So chloroform and methyl acetate form maximum boiling azeotrope. Does anybody remember what that means thermodynamically? Does it mean that they like being mixed or they dislike being mixed? In the simplest of terms.
Favor mixing.
What's that?
They favor mixing.
They favor mixing. Okay? So it actually reduces their volatility when they mix, as opposed to increasing their volatility when they mix, which is what's happening with the minimum voltage. Okay? All right. Let's do the edges. So the edge going from methyl acetate to methanol, these are the easy ones. So the minimum boiling azeotropes are these two. What's the direction of the arrow from this azeotrope up to methanol? Is it up? Good. It's up, okay. What about here, going from the methanol, methyl acetate azeotrope down towards methyl acetate? Is it down or up? Down. I'll save this one for later. Between methanol and the methanol chloroform azeotrope, does it point towards methanol or the azeotrope? Okay. They're all going to be either minimum boilers or maximum boilers, okay? Except for this, there's a couple of very strange examples. But anyway, okay. So methanol azeotrope to chloroform, up or down? Down. And then here's the unusual one. What's happening here? What's going on between the methyl acetate and methyl acetate chloroform azeotrope? Does it go left or right? It goes right. And what about chloroform to the methyl acetate chloroform azeotrope? Left. So what is methanol? Oh, sorry, the ternary. Hang on. The ternary has point of 56.42. Okay. What is chloroform? Say loud. Salad. And what is methyl acetate? Salad. So, rule 2A, N1 plus B in this case, what's B? Hang on, let's just do all of these. N1 is what in this case? 1. S1 is what? 2. B is what? How many binary trips do we have? 3. Okay, so N1 plus B, is it less than 4? It's not less than or equals, it actually is less than. Is it less than 4? No. Okay? Now, is the ternary the lowest, second lowest, highest, or second highest? No. Are the two lower than it? .76, 53.36. Are the two higher than it? So methyl acetate, methanol, the maximum boiling azeotrope, and chloroform are all higher. So that means that this ternary azeotrope is what? Saddle. Okay. So now what? N3 is now what? How many ternary 0? S3 is what? 1. And now, I'll just write this rule again. You have it in your notes before, I just want to 2 plus B minus N1 minus 2 N3 plus 2S3 all divided by 2, and that's equal to 2 plus 3 minus 1 minus 2 times 0 plus 2 times S3 all divided by 2 gives me 2 plus 2 is 4, minus 2 is 2 divided by 2 is equal to 1. So N2 is 1, meaning that S2 is equal to, how many saddle, how many binary azotropes or saddles? 2. Now you have to do some thinking. This is where the puzzle part comes. Which one do you think is the node? Go ahead. Did I make a mistake? Uh-oh. That would help. I didn't do this in my notes, so I'm like winging it. Okay. Making mistakes. Thank you. So that makes this easier. What's S2? 0. So then that means that all of the binaries are nodes. Okay? Well, I haven't drawn this one in a while. Okay. So what kind of node do you think this is? Stable. What kind of node do you think those two are? Just give me the reason. You guys are all correct. Why? Quite straightforward. What's up? Yeah, and these are the lowest boilers in the system, right? So they're going to be the unstable, and this is the highest boiler. Can you draw it? All right, try it. So the question is, how many boundaries are there, and how many regions?
That's 70 quarters. Missing kind of. That's good.
Okay, so, anybody want to give you suggestions? Okay, first of all, I'll ask the final thing first. How many regions does this have? All right, let's see. I'll put right in your margins. How many regions do you think this has? It's like the clicker question. The only way to really get it is by drawing it. Okay, so everybody got a number in the margin? Okay, we'll start. 1. How many people say 1? How many people say 2? How many people say 3? How many people say 4? Okay. 1, justified. Who said 1? Go ahead. You can pass.
I think we can align from the ternary azeotrope down to the high boiling azeotrope.
Okay.
And then I couldn't decide if I wanted to put a line up to the top from that as well. So I think it's going to be like one kind of like upside down heart shaped region.
1, that's okay. 2s? Yeah, go ahead.
I have lines, my resident curves coming out of the unstable nodes,
Yeah.
and then, kind of like a boundary between drawing from those to the ternary azeotrope.
So you have boundaries like this. Like that? So those are your 2.
And then I have curves
Okay,
going to
got it.
the,
Okay, I'll add curves in a second. Okay. Where was your boundary?
So it's like straight down to the bottom.
Okay. 3s. Who's a 3? Someone voted 3. Go ahead. Do you have the same boundaries? 4s. Go ahead.
one from like this ternary to the top.
No, that's the tricky one. Okay? But this is the answer after you draw the lines. Okay? So if you draw the lines, first of all, let's just connect the unstables to the stables. Remember, okay, I need different colors. Okay? I'm now drawing residue curves. I'll make these bold in a second. Okay? Just bear with me. This is the method here, so we're just going to connect these. Okay? That's hard to connect. It's on an edge. It's already there. Okay? What's happening in these saddles, this is quite easy. It's going like that. What's happening towards this saddle here? Remember how we go towards saddles and then you have multiple lines and they split? So it's quite, you can see that it's going to do something like that. And this is why they saw that boundary. Okay? Now what about this top line here? What's going to happen as we go towards this saddle? Are we going to go, if we're in this space, we're going to go from from this azeotrope, from methyl acetate azeotrope to methanol, we're going to go up like that, because we're going to go towards the saddle and split in the other direction. So it's going to go like this, and like that. There's an extra line right here. So this system has 1, 2, 3, 4 regions. What can you produce as products? Can you make chloroform or methyl acetate with a simple column, with a simple 2-product column? Can you make those? What are our choices for products in this system? Again, it's only going to depend on the feed location. Okay, so if we're in here, what can we make? Methanol as azeotrope, or not and. If we're in this system, can we make, again, methanol of that azeotrope? What are our choices here? We're stuck making azeotropes. Okay? You can make, if you're in region 3, you make this is the distillate, or this is the bottoms. If you're in 4, you can make this is the distillate, this is the bottoms. Can you see why azeotropes cause problem with distillation? Okay? So this is even more confounding than ternary. Let's do another example. I wanted to get into extractive distillation, but we'll see. All right, so now let's do this this way. I'll I'll do this example, if I don't get to that example, I'll do it at the beginning of next lecture. I just want you to start thinking about entrainers, okay? So let's talk about the different, let's just very simply, I'm going to just talk about generic entrainers at first. So if we have a minimum boiling azeotrope, between species A and B, and we're going to add an entrainer E. And entrainer E could be any number of things. Where can its boiling point be in relation to A and B? It can be the heavy, right? So it can be higher than A or B. It could be an intermediate. Or it can be a light. Right? So you can have an entrainer that's heavier than, let's make B be the heavier than A. So A has a a lower boiling point than B. The entrainer can either be heavier, intermediate, or light. So we can have three pictures. Let's just do this. Oh, I'm missing something. We're going to add no more azeotropes. We're going to make that a minimum boiler. Okay? So the azeotrope is a minimum boiler. If we have an intermediate entrainer, it's going to look like this. And our minimum boiling azeotrope is going to be here. And if we have a light, like this. So this is, let's just call that. It's a light entrainer. This is a heavy entrainer. And this is an intermediate. All I want to do now is draw the residue curves. How we're going to actually build the columns to do this kind of separation, I'll do next time, and I'll do it with examples. At the moment, I just want to do the residue curves so you can begin to see why the residue curves are useful, okay? Let's start with intermediate. This is a minimum boiling azeotrope. So what are the directions of the arrows? Okay, so B is heavier than A, and in this particular case, we're picking an entrainer. Let's call this entrainer I, entrainer light L, and entrainer heavy. So these are all different species. The A and B are the same species. Which way do the arrows go? Is the minimum boiling azeotrope, do they go towards the azeotrope or towards B, the binary of the pair? Do they go left or right? Left. Does it go left or right here? Right. Thank you. Does it go up or down between B and E? In this case, if E has a boiling point between B and A. Down. And up or down here. Does everybody follow that? Does everybody follow how we did that? This is just, we just picked an arbitrary entrainer. Okay, one thing to think about, how many intermediate entrainers are going to be, how hard is this going to be to find? There's going to be the least number of these. Okay, these are hard to find, so you've got to be between the boiling points. What does this picture look like? What's B? Is this heavy, is this stable, unstable, or saddle? What's A? What's E? What's the entrainer? There's no ternary. So if N1 is what? In this case? Which I want how many pure component nodes? S1 is equal to, how many pure component saddles do we have? 2. Okay. N3 is equal to S3 is equal to 0. So N2 is equal to, and I never get this memorized in time. 2 plus B minus N1 minus 2N3 plus 2S3 divided by 2, and it equals, in this case, 2 plus 1 minus 1 minus 0 plus 0, all divided by 2 gives me 1. And so that S2 is equal to what? In this case, there's only one azeotrope, so therefore S2 is what? And that means that a binary azeotrope in this picture is a what? Unstable node. How does it relate in terms of boiling points to all the other species? Go ahead.
Lowest boiling.
It's the lowest boiler. Because our lowest pure component species is A. And this binary is a minimum boiler, so it boils lower than A by definition. Therefore, this is an unstable node. What does this picture look like? Yeah, go ahead. Go ahead. I know how to just see if you can explain it.
Well, I guess like the two most extreme cases, one goes straight to B, and then the other one would go, I guess, towards A, towards E, down to B.
Great. And if you want to make it pretty, you just put one in the middle. Okay. How many regions with an intermediate in trainer? How many regions do I have here? How many boundaries? Not 0. Oh, well, okay, you're asking different questions. Okay. How many regions do I have? 1. Is there anything that's not feasible really here? Okay. Hold on to that for now. Let's do the heading. So there are no boundaries in there, so it's doable. Up or down from B to E. Now we're having an entrainer that's heavier than B. Okay, it's not in the middle anyway. Pick a different entrainer, it's an entirely different chemical species. Down, left or right, from A to E. Left. Up or down from the azeotrope to B. And up or down. Okay. So what is E in this case? What is A? And what is B? Okay, now I have to write the equation again. So N1 is what in this case? Still stays the same. And S1 is equal to? No? How many pure component saddles? 2. Okay? And then we know again S3 and N3 are 0. So N2 is equal to 2 plus B minus 1 minus 0 plus 0 divided by 2, and again it's equal to 1. So here, what is the azeotrope? It's unstable again. Okay? What does this picture look like? Go ahead.
There's going to be two regions. There's boundaries between the line between the unstable node and the stable node.
Boundaries have to have what on one end? Saddle. Go ahead.
So it's going to do from the azeotrope, it's going to go up to B and down to B. And then same thing with A to E, and then directly from azeotrope to E.
You can draw a residue line, not a boundary, just a straight. You can just go straight from the azeotrope to the entrainer. How many regions here? 1. Don't erase in your head yet those. I want to do this before I run out of time. And this will lead me to the next lecture. Okay, quickly now. A and B, up or down? Okay, again, let me just make sure you're on the same page. This is same A and B, same minimum boiling azeotrope. We're now adding a third entrainer that's lighter than A. Okay, so it's a light component. Up or down? Up or down? Left or right? Up or down? Okay. Just by definition. What is E? Node. What is B? And what is A? N1 is equal to? What's that? 2. S1 is? What is it? 1. Thank you. N3, S3 is equal to 0. N2 in this case, a little different. It's 2 plus 1 minus 2. Wait a second. That's not right.
0. S1 is 0. Yeah, it should be N1 equals 3. S1 0.
What did I do?
N1 is 3.
Sure, it's fine. N1 equals 3, and that's.
Thank you. Thank you, thank you, thank you. Glad that you're paying attention, because I'm not. Okay. Is equal to 0, meaning that S2 is, so what is the saddle? I mean, all right. Okay, so the azeotrope saddle, what does this picture look like? This is like my, in a way, my punchline for my lecture here. You want to do it again? Go for it.
There's two regions. There's the line is called. There's
Tell me what the picture looks
okay.
like.
E goes to A, and like at some point it goes towards the saddle for one of them, and then E goes to B.
Something like that? So what happens between E and the azeotrope in this case? Just hang on for 1 second, okay? Go ahead.
Boundary line between E and the azeotrope.
That's the answer to the question.
Is that always the case when you have unstable node and a saddle azeotrope? Is that just
Coincidence. But what's not a coincidence, now I will show a counterexample to this. Don't draw too big a conclusion here. But in a system with one binary azeotrope, can you use a light entrainer? Think about it for a second. If I wanted to say my feed stuff, remember I've got a mixture of A and B, and I want pure A and B. That's my goal. I want one stream of A and one stream of B. I'm going to start here. Can I get any product that's going to allow me to get A out of this by distillation? My choices of products are what? I can either get B in what side of the column? Coming out of this, I can get it where? Bottoms, or E out of the distillate. But where am I going to get A? Can I make A? Similarly, if I have this mixture, by adding E, am I going to get anywhere where I can make B? What I will show you in the next lecture is that an intermediate in boiler is wonderful, and I can draw a system where I give you a feed either here or here. We can add this material and get a pure stream of A and B. I'll show you how to do it next lecture. Similarly, with a bit of clever design, just hold on for 10 seconds, we can do something called extractive distillation and get it so that we can get pure A and B with a system with a heavy entrainer. What's the problem here? There's one nice thing that we have here going for us. Can you see what it is? What's the difference between that one and that one? Look at the pure component goals that you have. We've got a mixture of A and B. You want two A and B streams. What's the nice thing about this one? It makes this one a little harder. Anybody see it? You see the difference? They're both doable. Yes? Because why? You're right. Both of these are saddles. Because both these are saddles, you can't make them as products with simple columns. I'll show you how to solve that problem. This one is easy because you can make B. Okay? So these are both doable. This is where residue curves are useful. We can see that you cannot use a line trainer to solve this problem. Okay, that's it. End of story.